Hi, everyone. Thanks for everyone who comes on Friday afternoons at 3 p.m. to class. It's always appreciated here when I'm not talking to myself. And also, as your reward, you get to look at the pretty Saturn ring slides all day today. So, this really works for both of us. Um, I will say, due to popular demand, I think you should have all gotten an email that the final exam study material is on the Canvas website. So there's some practice quizzes. I highly recommend taking those quizzes in conditions that are similar to the exam. You get multiple tries on them because I know people probably want to try them more than once. But do try to study first, write your study sheet first, and then try those questions. I mean, it's not a complete perfect replica of the exam. Of course, the exam is going to be in here. It's going to be cumulative, but I just wanted you guys to have a rough idea of what level to reach for. And I'm definitely writing questions that are just very similar to the homework and quiz questions for if people are looking at what they want to do. Study guide is up there for the course if you haven't seen that yet. And yeah, please reach out to me if you have any other questions or concerns on that. Yes, projects we've been grading. They've been looking pretty good so far. Yeah, so everybody who submitted on time should have enough time for a regrade or to resubmit for a regrade, which is going to be due next Wednesday. Next Wednesday, for the record, the university requires us to hold a class, even though I know a lot of you have travel plans and things for the Thanksgiving holiday. So we do have a quiz that's going to go live after class on Monday, as usual. But then, so the first 15 minutes will, of course, be the quiz time for those who show up if you want to collaborate. If you can't make Wednesday, just do your 2 tries beforehand by yourself. Of course, that's by now the drill. And then the rest of the class, Miranda will be leading a review on Wednesday. Yes, and probably showing some cool YouTube videos, things like that. So it's not a very serious class. It's definitely an opportunity if you want to have a little one-on-one time studying a particular topic. It's a great excuse for that. But just so people know what's going to be happening on Wednesday. And if you're wondering if you want to come for the quiz and then maybe leave or something like that, that's the way it's going to be. But today we're going to talk about Saturn's rings. And we're going to talk about the rings of the other planets in the solar system as well. But Saturn is, of course, the most detailed of the ring systems, the most elaborate of all the ring systems that we have. This is a picture that was taken by the Cassini probe, which basically was 2004. It entered the Saturn system and it was there till 2017. So most of the beautiful Saturn images, if you ever see an image up close, it's usually from that Cassini mission. And this image was taken by the probe when Saturn was directly in front of the sun, eclipsing the sun from Cassini's point of view. So it backlit the planet Saturn and it gave us this incredible view of the rings. Some of these rings are very faint. They would be very hard to see if you didn't have them eclipsed by this planet Saturn. And fun fact, somewhere over here, there's a dot, which I don't think you're going to see on the screen because the brightness contract is not right. But the Earth is on this as well. If you really zoom in, apparently you can also see the planet Earth. So we're going to discuss these rings today, how to make rings, how we think rings this particular ring system originated, all sorts of things like that. So to start off, rings. First, I thought I would have you guys have a little discussion with each other. So how would we maybe figure out whether Saturn's rings are one solid piece or a swarm of moonlets? So what I mean is you can imagine the first time astronomers went and looked with a telescope, you see this feature, you don't know, is it a disk? Is it solid? Is it part of particles? How could you maybe figure this out? Yeah, so is the light maybe passing through them differently? Because then you might have some if there is a lower density bunch of little materials over one material. That's a good one. Yeah, for sure. We've definitely measured that. Anybody else have any ideas? Moving at different rates. That is actually a very important one. And this is the first way we measured it more directly. If a ring is composed of individual objects over being a solid structure, then the inner objects will orbit faster than the outer ones. This is thanks to Kepler's third law. And this has been measured. It's actually an easier measurement to make. Just look at the entire ring, how it's moving over looking at the individual parts of the ring. So this is how we know that the Saturn is actually made up of a lot of different objects. We're going to discuss them over just one solid structure. So how do we figure out how the rings work and things like that? So Galileo was the first one to observe Saturn when he looked at Jupiter. Of course, he looked at Saturn through his telescope in 1616. And he thought Saturn was a triple star because what he could basically see with his telescope, it was basically worse resolution than a modern pair of binoculars, but it was still better than, just your eye. He saw something like this. So he saw a structure here, and it's kind of like Mickey with the ears on the side. He saw two lobes. So he said that there was a triple star, unlike, moons or something like that, but he didn't understand why some of the smaller bodies sometimes disappeared over, you looked for many years. Sometimes he saw these structures, sometimes he didn't. He didn't really understand it. Who ended up changing this was an astronomer named Huygens in 1659, a Dutch astronomer. And he noticed that, he had a better telescope. So, okay, it's actually a ring structure. And what we're seeing with the rings is they will have a different inclination to us at different times of the orbit. And it has to do with the position between us and Saturn's rings. Saturn's rings are tilted because Saturn is tilted in the sky. So we don't always have the same vantage point toward us. So for example, when the rings are at maximum tilt to Earth, this is actually what it looks like. You'll see the ring structure not just exactly on the equator. You're going to see it tilted quite a bit to Earth, and they're going to be very, very prominent rings. The interesting fun thing for right now is the rings are actually at this point of disappearing. They do it for a very short period of the orbit. I told you guys earlier, Saturn has a 30-year orbit, so you can imagine the line of sight has to be pretty perfect for us for them to disappear. It's actually happening right now. And by right now, I mean Sunday, is the day that it's in this period expected to disappear completely. So this is a artist conception. So, 2 years ago, last year versus now. Basically, if you look at Saturn, the rings are so thin, they will be basically disappearing. And it's like a couple weeks tops that you have this phenomenon. If you want to look, I don't know how many people are local versus traveling for the holiday, but the Eugene Astronomical Society has a star party that's going to be the Friday after Thanksgiving in Emerald Park. I put the link here so you can go to the slides if you're interested in going. If it's clear, they'll have telescopes. You can go out and you can look at Saturn and be like, okay, there's definitely no rings there. So, but this is a pretty unique feature. There's some moons, for example, you can only see when this happens around Saturn from Earth, and all sorts of things like that. It's also worth noting that we actually have rings around every outer planet. I'm pausing now to say this because we're going to be discussing Saturn in such depth for the rest of this lecture. We do want to point this out. So Jupiter has a very faint ring system, not really much to write home about. It's very, very difficult to see from Earth. Uranus and Neptune also have a faint ring system. The Uranus one you can see because of the tilt of the planet much more easily from Earth. Neptune, we basically only know because Voyager saw it, Voyager 2, when it went to the system. Those other ring systems are very faint and very dark and narrow compared to the Saturn rings, which are very bright and wide, and that's why they really capture our attention. What rings are made of? Rings are mainly made of water ice. So darker material, so as I said, like Jupiter, Uranus, Neptune, those smaller rings, they're basically carbon compounds and usually kind of dusty material is the way to think of it. But Saturn's rings, because they're so bright, it has to do with the fact that there's such a high content of water ice present in those rings. The ring particles themselves are very small. Most of them are sand grain, couple centimeters tops in diameter. You can have some larger chunks that are more house size, but for the most part, pick up some grains of sand, and that's more on par with what we have for the rings of Saturn than anything more significant. You, of course, have some moons as well, but we'll discuss the interaction of the moons with the rings. The point is ring material is not moon material. They're very independent type of objects, we think. So I said it's very small. So there's also a slight distribution of what you'll have for these rings. So this is just a sense of scale. So this is a false color image of the rings, but it's color coded to the size of the particles. So the reds, for example, are going to be the regions with particles larger than 2 inches, green 1 to 2, and then blues are going to be the regions with smaller than 2 inches particles. So you can see different parts of the ring structure will have different features in them for what exactly we see. Finally, yeah, so as I showed this slide on Monday, but there's also the icy moons of Jupiter. They're, for the most part, further out than the rings themselves. The rings are pretty far in compared to these icy moons that are the more larger moons in the Saturn system. Moving on. The ring structure of the rings. The first thing to note here is the rings are very flat. And I mean, I already said they're flat enough that they can disappear from Earth. But when I say flat, I mean only about 30 feet thick, which if you think of the size of the planet, I mean, even on Earth, that would be like nothing. There's some parts that can be a little thicker, but definitely no more than a kilometer in thickness. That would be a very, very thick part of the ring, for sure. The second thing we can see for the rings is that there's quite a bit of structure in the ring system itself. What I mean is, if this is Saturn, we're kind of looking from the top. You can see the cool hexagon there. You can see there's one main gap here between the inner and the outer rings. So this is actually called the Cassini division. The Cassini mission was named after Cassini, who was the first astronomer to notice that there's a gap in Saturn's rings. But then when we go into even more detail, if we look at a really close part of those rings, this is the highest resolution image that has ever been captured for the Saturn's rings by the Cassini mission. So the resolution here is like about a mile, 2 to 3 kilometers in resolution. And what we can see is each of those rings is actually even more smaller rings subdivided, right? It's an incredibly complicated structure. I lost this screen here, so I'm gonna, this is weird. Oh, it's back. Hello. Yeah, I see it's there, but it's not here. And I like to see what I'm talking about. Okay, yeah. So the ringlets in the center in the center of this image are about 25 miles wide. If we're looking at these features here, the broader bands are maybe 200 to 300 miles wide. So there is some variety in how these ringlet bands work, or the sizes of them. But the point is they're very, very flat structures. There's a ton of them going out to very great distances from Saturn. So several times the size of the planet itself for this ring structure. So here's a question for you guys. This question has 2 correct answers and 1 incorrect answer. So I'm going to ask you guys, which one do you think is not true? Why do you think there are gaps in Saturn's rings? So which one of these do you think is not a correct answer for that? So the correct answers are actually A and B, and C is not correct. This Saturn's ring system is huge, but the fact that Jupiter is far enough away to not affect the structure that we see. This is all has to do with what we're seeing around the planet Saturn. And the answer is that there are some gaps that are in resonance with one of Saturn's moons. So it could be one of the moons further out that we were discussing, those icy moons. But there's also some small moons that are present in those rings and will also clear out some of those gaps. So, for example, this is another gap. It's called the Encke gap, which is named after another astronomer who discovered it. And it's cleared by a moon named Pan. There's actually a very small moon compared to the icy moons running around in there. Think more asteroid-sized over proper moon size. And as it's going around, it will affect the little bits of dust. It'll either accrete that dust or kick that dust out into another orbit, and that is going to affect things. So orbital resonance, I mean, we've talked about this a bit last class with the Jupiter system, but just to discuss this a little bit more, imagine we have 2 objects that are orbiting the same planet. These are both actually moons of Saturn, I believe. And their orbital period is related by a ratio. So one orbits every 2, for every 2 times one orbits 3, 4 to 5, things like that. What this is going to cause with orbital resonance is when they're coming, these objects are going to move away from each other over time. And this is just because, of course, when gravitationally they're going to be affecting each other, they're going to be kind of pushing each other apart as well each time they're passing close to each other. And then what's going to happen is when these objects are in orbital resonance with the moon's gravity is going to destabilize that orbital distance, and it's going to clear out these gaps. So here's another example of a moon of Saturn. It is called Mimas. Mimas is cool. So it's here. It's the Death Star moon, right? Because it has that big one giant crater on it. And so the Death Star moon, Mimas, causes the Cassini division, that biggest gap that I was telling you guys about. It's going to start orbiting inward whenever it's in resonance with another moon. And over time, it's pushing that gap and clearing that space. Orbital resonance is not the only structure or the only type of way that icy moons can interact, though. There's another very cool one called shepherd moons. So this is a moon on this GIF here. which is called Prometheus. And then there's another ring there called Pandora. These are both pretty small moons, so they're about 50 miles across, 80 kilometers, something like that. And what happens though is they're in two orbits pretty close to each other. I mean, they are in some sort of locked, like one is fault trailing the other. But what you can see is they're what's called shepherd moons. So a shepherd moon is when you have two moons that are basically keeping the material in a ring and line. We'll watch it again one more time. So you can see the moon is going upwards there. The other moon is going there. You can see there's a change in the material when it's closest to there. So it's keeping that material in a very discrete band around the planet. And these thin bands are then formed from the two planets, or sorry, the two moons that are staying in line there. This is what's called the F ring. It's one of the most thin rings in terms of width in the Saturn system, and has to do with the shepherd moons that are present. It's kind of tough to see in the GIF, but we also will see structures in the material itself from these shepherd moons. So this is a shepherd moon called Daphnis. It's basically a fancy asteroid that is a moon. And you can see actual ripples that are created in that gravitational, the material from the ring. And that is due to the gravitational ripples caused by that moon itself as it's orbiting Saturn. So I think this is a pretty amazing level of detail if you're looking at this, that we can actually see the waves in the material as these rings go around. The other cool one we have they're called ravioli moons. So these are the moons. A lot of them are shepherd moons or similar moons, but there's also, as I said, a lot of like dust grain size things that are going on in Saturn's rings. So the ravioli moons are the moons that are basically coated by this material. I mean, you can imagine you're orbiting, the rings are orbiting, you're going to get dusty, right? Like over time. And we can actually see this. So look, for example, up here at Atlas. I mean, it looks fuzzy, right? We've seen enough images by now from space that that's normally not what they look like. A lot of these other ones may be harder to see, but they all look a little bit fuzzy is kind of the way to think of it. Atlas is definitely the most clear case of this. And this is basically just the moons are accreting material. It's not really accreting. It's kind of like dust just going on, and nobody has a giant vacuum cleaner to go clean them up. So that's what they look like. Another ring feature that we see are called spokes. So we can't see these from Earth, but we've seen them with Voyager, Cassini. Okay, the Hubble telescope, I guess we can. If you have a space telescope near Earth, you can see them. And these are clouds of dust particles on top of the B ring in particular is where we see them. And they actually, you will see spoke structures. So, spokes like your bicycle, you can imagine the ring going. You will see these changes over time in the ring system. They only appear in one of the rings called the B ring. And they also only appear during Saturn's equinox every 14 years. So we think that the conditions are right only during that specific moment of the Saturnian year. You can have a lot of different things that are happening in those spokes. So you have dark versus light spokes. And that has to do with, is the ring brighter than the spoke, or is the spoke brighter than the ring? This has to do with the dusty material and how it's moving at this particular point. Making a ring. Okay, we've discussed a lot of features of the rings, but how do you make one in the first place? So close to planets, tidal forces can be so strong that objects that get too close will get torn completely apart. We haven't discussed this too much in this class. We have tidal forces, of course, the moon versus Earth's, and we see that with our oceans. We discussed how you can have extreme tidal forces on Jupiter's moons, causing volcano planets, things like that. But you can also have tidal forces if you get close enough to a thing that it will eventually just tear apart the body completely. It has nothing to do with this class, so I haven't been able to show you guys cool pictures of it. But one of my main research things, for example, is actually they're called tidal disruption events. And it's when a star wanders too close to a black hole and gets shredded basically by the forces around the black hole. So that's a very extreme cosmic example that does not happen in our solar system, but this does happen in a lot of different cases in astronomy, that something can get too close to another object and then the tidal forces will tear it apart. The way this works is you have your moon going too close. It passes this tidal radius here, and it is going to break up into a lot of different pieces. And it is going to then eventually form some sort of ring structure or accretion disk in the case of a black hole, which is kind of a fancy way of saying a ring structure, I guess. But yeah. This is defined by the Roche limit, which is the closest distance to a body, a planet or star, where a large object can orbit. You can't have an object orbiting too close to a larger thing, or else it's just going to break apart completely. So I'm going to show you guys equations. Once again, you're not going to have to use these equations on the exam or anything, but we do want to understand where these concepts come from. So if we have the main body's radius, which here in the image, so this is a star, I think, that's disrupting a planet. So the radius of that larger mass, and then the main body is going to have some sort of density, which is going to be this upper term here. And their satellite density is going to have another term. Then that is going to give you the distance to the Roche limit. This is if it's a rocky object that is being disrupted, and that it is going to change based off of the material or the density of the object that is being disrupted. So if you had an icy object, which is much less dense than a rocky object, you can see that this coefficient term in the front ends up making the distance larger that you need for an icy object to get disrupted than a rocky one, even if everything else is the same. So just as a quick question to see if people are following me, are you more likely to find rocky or icy moons closer to a planet? Here are the two equations I just showed you guys. Thumbs up or thumbs down? All right, thumbs up. I see a lot, so excellent. Yes, so rocky planets are going to be closer to a planet than an icy one. It's going to break up further out. So if we think about this icy Roche limit, and we have our distance here to the center of the planet, we have our icy structure coming in. The icy objects entering inside the Roche limit are broken up into smaller pieces. Versus if we have the rocky one, it's going to go much closer, and the rocky objects entering the Roche limit are then broken up, but at a much closer radius to the planet. You guys are going to be exploring this a little more in the activity today. I think the activity today is, so if you had Mars, which has two moons, Phobos and Deimos, one of those moons is going to eventually come close to Mars on its orbit as we see it. So the question is going to be, you guys are going to figure out, is Mars going to have a ring someday based off the Roche limit and its current moons? Before we do that, though, I have one final thing that I wanted to get to, which is, okay, what caused Saturn's rings in the first place? And the reason this is a good question to ask is we've actually learned a ton about this in recent years and really changed our understanding of what exactly has caused the Saturn's ring system. The reason is, I mean, there's two obvious options. One is the rings could be as old as Saturn and have been around for 4.5 billion years. The second is that the rings are younger. If, something is as old as that, then why does Saturn have the rings? Why do other planets not have as significant rings? Things like that. But good news for astronomers, we think we finally know the answer to this to some degree. So this is the Cassini mission here. This is an artist's conception. We don't actually have this picture, of course. But as I said, it ran for many, many years. It was over a decade that it was in the Saturn system, about 15 years. But eventually you're going to run out of fuel. And you're not leaving a space probe up there. You're going to have it crash into Saturn or something like that. Because I told you guys, there's geysers on Enceladus, there's things like that. We don't want to risk contaminating other moons by accident that might have life on them. In 2017, so it ended in September 2017 was the month that Cassini ended, but they were like, okay, we have a space probe. We're going to start doing some things that would have been way, way too risky at the beginning of the mission, but by now, why not? And what they ended up doing with Cassini was they sent it on an orbital trajectory that actually went through the rings 22 times or so, and basically take detailed measurements of those rings that were impossible to take until you actually have a space probe going there. There's two things you can do. First of all, you can measure how bright those rings are at very, very close distance. The second thing you could do is measure how fast and how slow the probe is, so what acceleration is as it's going between the rings and Saturn, and figure out from those observations what the mass of Saturn and what the mass of the rings has to be. So as I said, this is something crazy you would never do at the beginning of the mission, but by the end of the mission, it's like, okay, we really actually want to know the answer to this. So they did it. And it was fantastically successful. What we ended up getting from this gravitational data and from the age of the rings is that the rings are just 10 to 100 million years old, which in the grand scheme of our solar system is really not that old. I mean, dinosaurs went extinct right before this. Sharks are older than Saturn's rings. Trees, I think, are also older than Saturn's rings. So very, very recent in the grand scheme of things. It is worth mentioning the brightness of the ring material is actually a cool one. So as I said, they're mainly ice. But you have some dust that's just floating around over time. Any surface is going to get some dust on it in our solar system, just because of all the micrometeorites out there, things like that. So basically what they were doing is they were measuring as they were going close to these particles, how bright the icy bits were. And because over time they would have a certain amount of dust on them. And from that coding, they could conclude that the rings have to be only, tens of millions of years old or something like that. Some studies suggest they could be up to 400 million years old. I think the point to drive home here is they're not 4.5 billion years old. That's pretty clear by now. It is also interesting to note that the ring ice over time is actually dissipating into Saturn because it's, within that Roche limit. Some of that ice every year then drifts further in and gets absorbed by the planet. So we think, based off of current estimates, that we only have about 100 million years left that we have Saturn with rings that are any large size. I mean, there's still probably going to be some small amount, but it's going to be like Jupiter where it's like nothing to write home about. So we're actually in a very, very lucky period of time that we actually have these beautiful rings and, lucky time to be alive if you really, really like the planet Saturn. Okay, so how are you going to get something like a giant ring in the last 10 to 100 million years? The most likely theory is that you're going to have some sort of impact. So what I mean by this is imagine one of those icy moons that we now have them further out, but there was one that was a little further in, close to that Roche limit, not quite past it. And a comet came in that was large enough to just completely obliterate that moon. And what we see now is the material that's left over from that is basically still orbiting in that ring structure. It can't reform because that's too close to the planet for the most part. So here's a simulation of what this might look like. I actually know the guy who made the simulation. So we have our moon here. We have a comet that is about to collide with the moon. And it is going to basically completely obliterate this moon. You're going to have an expanding cloud of very icy fragments that is going outward very, very quickly, destroying this moon, the original moon. And it's going to take a few seconds to evolve, but it is a very rapid process, though, overall. Like you'll see, it's only going to take us a few hours to have a ring structure in the surrounding Saturn. So, all right. Let's give it a minute. Okay, we speeds up now. Cool. So yeah, you have this collisional debris. It's going to go along the moon's orbit, and it's going to lead to the formation of a ring surrounding Saturn. And yeah, I mean, we could keep watching it, but you could see within a few days, you're already going to have some sort of ring structure. Astronomers definitely are still quibbling about the details of how this process would work, how things would impact. Turns out it's a very tough simulation to run. Shocker, there's a lot of different things to keep track of. But you do get this ring structure relatively quickly surrounding the Saturn. And as I said, from if you had this case of an icy moon that had a comet impacting it. So most likely this happened in the astronomically recent past for Saturn. Does make you kind of wonder if maybe this happened for Jupiter at some point. Maybe Jupiter had a cool ring system, but it's long since dissipated, so we can't see it. But that's the general story of what we think has happened around Saturn.